Hey everyone, and welcome back for another deep dive. Today we're going to be tackling a question that's been puzzling, well, physicists, philosophers, really everyone, for over a century.
hmm
And that is the universe a perfectly predictable machine?
Okay.
Or is there, like, a fundamental element of chance at play?
Yeah.
And to help us kind of unpack this, we're going to be diving deep into the world of quantum mechanics
Oh,
and how it compares to classical physics. So
yeah.
our guide for this journey is going to be physicist Jörg O. Schneeppert and his essay, Quantenmechanik versus Klassische Physik, ein Vergleich.
So that's a
We're going to
mouthful.
be talking about all this in English, though, don't worry.
See, yeah.
Focusing on the key insights and what they mean for our understanding of reality.
It's a fascinating question, and Schneeppert really gets to the heart of it, I think. By highlighting the key differences between these two foundational theories of physics. It's a journey that takes us from, the familiar world of planets and billiard balls
Right.
to the mind-boggling realm of atoms and subatomic
Yes.
particles.
So let's start with what we know, the world of classical physics.
Okay.
We've all experienced it, you know, throwing a ball, watching the planets move across the sky. It
Yeah.
feels predictable, right?
Absolutely, and that's the core of classical physics. It's deterministic, meaning that if you know the starting conditions, like the position and speed of a ball,
Right.
you can, in theory, predict exactly where it will go and what it will do.
Okay.
Think of Newton's laws of motion. They describe how objects move and interact
Yeah.
in a way that feels very intuitive to us.
Right.
Then there's electromagnetism, which explains how electricity and magnetism are related,
Hmm.
and thermodynamics, which deals with concepts like heat and energy transfer.
Right. It paints a picture of the universe as this giant clockwork mechanism,
Yeah.
ticking along in a predetermined way.
Yeah.
But then, as Schneeppert explains, we zoom in and things start to get a little weird.
Yeah.
Enter the quantum world. What's the first clue that this classical picture, this clockwork picture, isn't the whole story?
One of the first major cracks in the classical framework came from something called the ultraviolet catastrophe.
Okay.
Classical physics predicted that a heated object should emit an infinite amount of energy at high frequencies, which is obviously impossible.
Right.
This wasn't just a minor calculation error, it exposed a fundamental flaw in our understanding of how energy works at the atomic level. It was like physicists had hit a wall.
So what happened? Did someone come along and smash that wall down?
That's where Max Planck enters the scene.
Okay.
To resolve this catastrophe, he proposed a radical idea. Energy isn't continuous,
Okay.
but rather comes in discrete packets, which he called quanta. It was a revolutionary concept that challenged the very foundations of classical physics, and it gave birth to quantum mechanics. Schneeppert really emphasizes how the seemingly simple idea that energy is quantized
Yeah.
has profound implications for our understanding of the universe.
So energy comes in tiny bundles. What does that mean for how we picture the world?
Well, think about it this way. Imagine trying to pay for something with only dollar bills. You can't give someone half a dollar bill or a quarter of a dollar bill. You're limited to these discrete units of currency. Planck's idea was that energy works similarly. You can't have any amount of energy, only multiples of these fundamental quantum growth.
Okay, I'm starting to see how this shakes things up a little bit. What happens next in this quantum revolution? Does it just stop with energy being bundled up?
Oh, not at all. Schneeppert takes us through the contributions of other brilliant minds who took Planck's idea and ran with it. Einstein, for instance, used it to explain the photoelectric effect,
Okay.
where light shining on a metal surface can knock electrons loose. He proposed that light itself is quantized, meaning it exists as both a wave and a particle, a concept now known as wave-particle duality.
Wait, light can be both a wave and a part. That doesn't make sense. Waves are like spread out, while particles are like tiny.
It does seem counterintuitive, doesn't it? But numerous experiments have confirmed this dual nature of light. And it's not just light other particles, like electrons exhibit wave-particle duality as well. This is one of those mind-bending concepts that really sets quantum mechanics apart from our everyday experience.
So we've got these bundles of energy and particles acting like waves. What other strange things are going on in the quantum world?
Schneeppert goes on to discuss Niels Bohr, who proposed a model of the atom
Okay.
where electrons orbit the nucleus in specific quantized energy levels. This explains why atoms are stable and why they emit light at specific frequencies when heated.
So instead of electrons swirling around the nucleus like planets orbiting the sun,
Yeah,
they're restricted to these specific energy levels.
exactly. Imagine the electrons are like passengers on a Ferris wheel. They
Wow.
can only occupy certain cars, not just any point on the wheel. This quantum model of the atom was a major breakthrough, but it was still incomplete.
What was missing?
Enter Erwin Schrödinger. He developed a mathematical equation that describes the behavior of quantum systems.
Okay.
It's not about predicting exactly where a particle will be, but rather about calculating the probability of finding it in a particular location. This equation, which Schneeppert refers to as the foundation of quantum mechanics, moves us away from the deterministic view of classical physics and into a world of possibilities.
So instead of knowing exactly where a particle is,
Mhm.
we only know the chances of finding it in different places. That sounds like a lot of guesswork.
It might seem that way,
Huh.
but it's actually incredibly powerful. Schrödinger's equation allows us to make predictions about the behavior of quantum systems. And these predictions have been experimentally verified time and time again. It's like we're trading the certainty of classical physics for a more nuanced and, frankly, more accurate view of the world.
This is already blowing my mind, and I have a feeling we're just getting started. What other wild ideas did these quantum pioneers come up with?
Well, Schneeppert highlights another crucial figure, Werner Heisenberg. He developed something called the uncertainty principle, which states that it's impossible to know both the position and momentum of a particle with perfect accuracy. The more precisely you measure one, the less you know about the other.
So it's not just about our limitations as observers. There's like a fundamental fuzziness built into the fabric of reality itself. That's pretty mind-blowing.
It is indeed. This principle challenges our classical intuition, that everything can be known with perfect precision. It suggests that there's a fundamental limit to what we can know about the universe at the quantum level. And it's this uncertainty that opens the door to some of the most bizarre and fascinating phenomena in the quantum world.
This is all so fascinating, but honestly, a bit confusing too. How can a particle act like a wave? What does it even mean to have a probability of finding a particle somewhere instead of knowing its exact location? And this uncertainty principle, is it just about limitations in our measurements? Or is there something deeper going on?
Those are all excellent questions. And honestly, questions that physicists are still grappling with today, but that's what makes this deep dive so exciting. We're venturing into a realm where our everyday intuitions break down, where the familiar rules of classical physics no longer apply.
Right.
And it's by exploring these mind-bending concepts that we can start to glimpse a deeper, more nuanced picture of reality.
Okay, I'm ready to keep going.
Yeah.
What else does Schneeppert have in store for us as we delve deeper into the quantum world?
You know, as we dive into these mind-bending ideas, what strikes me about Schneeppert's essay is how he emphasizes this historical context.
Right.
It's like he's saying, look, these discoveries didn't happen in a vacuum.
Yeah.
They were the result of decades, even centuries, of scientists building on each other's work, questioning assumptions, and daring to challenge the status quo.
That's so true. It wasn't like someone just woke up one day and said, hey, I think energy comes in tiny packets. These breakthroughs were born out of a need to explain experimental results that didn't fit the existing theories. It's a reminder that science is a process, a journey of discovery that's driven by curiosity and a willingness to embrace the unknown.
Exactly. And Schneeppert does a great job of highlighting this journey. He starts by taking us back to the giants of classical physics.
Yeah.
Newton, Maxwell, Boltzmann,
Right.
who laid the foundation for a deterministic universe
Right.
where everything in theory could be predicted. But then he shows how cracks began to appear in this seemingly perfect picture.
Right, like the ultraviolet catastrophe we talked about earlier. Classical physics simply couldn't explain why a heated object didn't emit an infinite amount of energy at high frequencies.
Yeah.
The clear sign that something was missing.
And that something turned out to be a whole new way of thinking about the universe.
Yeah.
Schneeppert makes the point that it was these seemingly small anomalies, these nagging inconsistencies that ultimately led to the quantum revolution.
Okay. It's a reminder that sometimes the most profound discoveries come from paying attention to the things that don't quite fit.
Absolutely.
Okay, so let's kind of unpack some of these key figures in the quantum revolution.
Okay.
We've already talked about Planck and his revolutionary idea of quantized energy. What about the others? How did they kind of contribute to this paradigm shift?
Well, Schneeppert spends some time on Einstein, who not only embraced Planck's idea, but took it a step further. He used it to explain the photoelectric effect, the way light shining on a metal surface can knock electrons loose. He proposed that light itself isn't just a wave, but also acts like it's made of tiny packets of energy called photons.
So it's like light has a split personality. Sometimes it acts like a wave, and sometimes it acts like a particle.
Exactly. It's this wave-particle duality. That's one of the most mind-boggling aspects of quantum mechanics.
Right. It challenges our classical intuition that
Mm.
things should be either one or the other. And it raises all sorts of questions about what light really is. I'm trying to wrap my head around this. It's like trying to imagine a sound wave that can also act like a tiny pebble. What happens next in this quantum saga?
Schneepat then introduces us to Niels Bohr,
Okay.
who developed a model of the atom, where electrons occupy specific quantized energy levels. Instead of electrons swirling around the nucleus like planets orbiting the sun,
Right.
they're restricted to these discrete energy levels, like passengers on a Ferris wheel who can only occupy certain cars.
So that's why atoms don't just collapse. The electrons can't spiral into the nucleus
Yeah.
because they're stuck in these specific energy levels.
Right, Bohr's model was a major breakthrough, but it was still based on a semi-classical picture, a kind of hybrid between classical and quantum ideas.
Okay. It wasn't until Werner Heisenberg and Erwin Schrödinger came along that the full mathematical framework of quantum mechanics was developed.
Yeah, that's right.
I'm sensing a pattern here. Each
Yeah.
of these scientists building on the work of those who came before them, pushing the boundaries of our understanding further and further.
Exactly. Schneepat does a great job of weaving together the scientific breakthroughs with the personal stories of these brilliant minds. It shows how science is not just a collection of facts and equations,
Right.
but a human endeavor driven by passion, creativity, and a willingness to challenge the status quo.
Okay, so we've got these quantized energy levels, this wave-particle duality. What does Schrödinger bring to the table? How does his work fit into this quantum puzzle?
Schrödinger developed an equation that describes how quantum systems change over time.
Okay.
Instead of predicting exactly where a particle will be, it tells us the probability of finding it in a particular location. It's like a mathematical roadmap that shows us all the possible paths a particle can take.
Right.
We don't know which path it will actually choose until we make a measurement.
So we're trading the certainty of knowing where a particle is for a probability cloud of where it might be. It's like saying we don't know exactly where a plane is, but we can predict the chances of finding it over London, Paris, or Rome at any given time.
That's a great analogy, and it highlights a key difference between classical and quantum physics. In the classical world, we assume that objects have definite properties that exist independent of our observation.
Okay, but in the quantum world, those properties are often undefined until we make a measurement.
Right.
That's where Heisenberg's uncertainty principle comes in, right?
Yeah.
The more precisely you measure one property of a particle, like its position,
Yeah.
the less you know about another property, like its momentum.
Exactly. It's like trying to catch a firefly in a jar.
Okay.
If you close the lid quickly, you might know where it is,
Yeah.
but you don't know how fast it was flying or in what direction. If you leave the lid open to observe its motion, you can't be sure where it is within the jar. Heisenberg's principle tells us that this isn't just a limitation of our tools.
Right.
It's a fundamental aspect of the universe at the quantum level.
Okay, so we've established that classical physics and quantum mechanics offer very different perspectives on reality.
Yeah.
But as Schneepat points out, they're not mutually exclusive. How do these two seemingly incompatible frameworks coexist?
That's a great question. Schneepat emphasizes that classical physics can actually be seen as an approximation of quantum mechanics.
Okay.
It works well at larger scales, where quantum effects become less prominent, like describing the motion of planets or the behavior of fluids.
Right.
But at the atomic and subatomic levels, we need the full power of quantum mechanics to understand what's going on.
Exactly.
It's like zooming out from a pixelated image. As you move further away, the individual pixels blur together, and you see a smoother, more continuous picture. But if you want to understand the details, you need to look at the individual pixels.
That's a perfect analogy, and it highlights the idea of decoherence,
Okay.
which Schneepat explains beautifully.
Yeah.
Decoherence is the process by which quantum systems lose their quantum coherence, their wave-like properties, as they interact with their environment.
Okay, it's like the environment acts as a filter, washing out the quantum weirdness
Yeah.
and leaving behind the more familiar deterministic behavior of classical objects.
So it's not like quantum mechanics only applies in some special isolated realm. It's the foundation of our reality.
Right.
But at macroscopic scales, those quantum effects get smoothed over by the constant interactions between particles and their environment.
Exactly. It's why we don't see macroscopic objects like chairs and tables behaving in a quantum superposition,
Right.
existing in multiple states at once. Their constant interaction with their surroundings forces them into a more definite classical state.
Okay, so we've got these two frameworks. classical physics for the macroscopic world, and quantum mechanics for the microscopic world. But they're not completely separate. Classical physics emerges from the underlying quantum reality, like a mosaic made up of tiny quantum tiles.
That's a beautiful way to put it. And Schneppat makes it clear that even though classical physics works incredibly well for describing our everyday experiences, it's crucial to remember that it's still an approximation. It's a simplification of a deeper, more fundamental quantum reality.
It's like we've been looking at the world through a blurry lens, and quantum mechanics has given us a sharper focus. We can now see the intricate details, the underlying mechanisms that govern the behavior of matter and energy at the most fundamental level.
Right, and Schneppat reminds us that it's this deeper quantum reality that underpins many of the technologies that
Yeah.
have revolutionized our world.
Right.
Transistors, lasers, medical imaging techniques like MRI, and the burgeoning fields of quantum computing and quantum cryptography.
It's incredible to think that this strange and counterintuitive theory, born out of a crisis in classical physics,
Hmm.
has led to such transformative technologies. It's a testament to the power of human curiosity, our relentless drive to understand the universe, and to harness its secrets for the betterment of humanity.
Absolutely.
But Schneppat doesn't just focus on the science. He also delves into the philosophical implications of quantum mechanics. And that's where things get really wild.
Oh, absolutely. The philosophical implications are where things get really mind-bending. Because if the universe at its most fundamental level is governed by probabilities,
Right.
and uncertainties, what does that say about our own existence? Our free will? The very nature of reality itself? These are questions that philosophers have been wrestling with for centuries, and quantum mechanics throws a whole new wrench into the works.
Right. If the universe isn't this deterministic clockwork machine that classical physics seem to suggest, does that mean the future is truly uncertain? Does it mean there's room for free will in a world governed by chance?
These are big questions, and Schneppat doesn't shy away from them. He explores different interpretations of quantum mechanics,
Okay.
like the Copenhagen interpretation, which emphasizes the role of the observer in collapsing the wave function, and the many worlds interpretation, which suggests that every quantum measurement splits the universe into multiple parallel realities.
Multiple universes. Okay, now you're just messing with me.
I know it sounds like science fiction, but it's a serious idea that some physicists take very seriously, and it highlights just how profound and challenging the implications of quantum mechanics are.
Right. It forces us to confront the limits of our understanding and to question our assumptions about what's possible.
Yeah.
So we've got these mind-bending scientific concepts,
Yeah.
these far-reaching philosophical implications. What else does Schneppat explore in his essay? Where does this journey through the quantum world lead us?
Well, Schneppat also touches on the ultimate goal in physics, finding a unified theory that seamlessly blends quantum mechanics with Einstein's theory of general relativity, which describes gravity.
Okay. It's the quest for a theory of everything,
Hmm.
a single framework that can explain the universe at all scales, from the tiniest subatomic particle to the largest cosmic structures.
Right.
Now, that's an ambitious goal. Has there been any progress on that front?
There have been promising attempts, like string theory and loop quantum gravity, but they're still very much theoretical frameworks, lacking definitive experimental verification. The challenge is immense, but the potential rewards are even greater. If we can find a unified theory, it would be a monumental achievement, representing the culmination of centuries of scientific exploration and a profound leap forward in our understanding of the cosmos.
It's like we're standing on the shoulders of giants, looking out at a vast, uncharted territory. We've come a long way from the deterministic clockwork universe of classical physics
Yeah.
to the strange and uncertain realm of quantum mechanics.
Yeah.
But the journey isn't over. There's still so much more to explore, so many mysteries yet to be unraveled.
Absolutely. And Schneppat leaves us with a sense of both awe and excitement. Awe at the profound implications of what we've discovered, and excitement for the discoveries that lie ahead. It's like he's saying, we've come a long way, but the adventure has only just begun. Buckle up, because the quantum world is going to keep surprising us.
Okay, I'm buckled in and ready for more. What else does Schneppat have in store for us as we continue this deep dive into the quantum realm?
So welcome back, everyone. We've been on quite a journey with Yurgo Schneppat's essay,
Yeah.
exploring the strange and fascinating world of quantum mechanics.
It's been a wild ride, that's for sure.
Yeah.
From the deterministic clockwork of classical physics to the probabilistic world of quantum mechanics, where particles act like waves, energy comes in bundles, and there's a fundamental limit to what we can know.
And as we kind of wrap up this deep dive, I think it's important to emphasize something that Schneeppet keeps coming back to.
Yeah,
These two seemingly contradictory theories, classical and quantum, are both essential for understanding the universe.
absolutely.
It's not about choosing one over the other, right?
Exactly. They each have their own domain, their own strengths and limitations.
Right.
Classical physics is fantastic for describing the macroscopic world, the motion of planets, the behavior of fluids, the workings of everyday objects.
But when we zoom in to the atomic and subatomic level, that's where quantum mechanics takes center stage.
Right, and it's not just about separate domains, right?
Right.
Schneeppet makes the point that classical physics actually emerges from the underlying quantum reality.
Yeah.
It's like a mosaic.
Yeah.
Up close, you see the individual tiles. But from a distance, it forms a complete picture.
It's a beautiful analogy.
Yeah.
And it highlights the interconnectedness of these two theories, the very properties of matter that allow for the existence of stars, planets, even us, are ultimately determined by the quantum behavior of particles.
Right.
And without the framework of classical physics to challenge and push beyond, we wouldn't have discovered quantum mechanics in the first place.
It's a reminder that science is all about building upon previous knowledge, questioning assumptions, and constantly refining our understanding of the universe.
Yeah.
And speaking of refining our understanding, I have to ask, with all this talk about the weirdness of quantum mechanics, does it ever make you question our everyday perception of reality?
It absolutely does. One of the things I find most fascinating about Schneeppet's essay is how he tackles the philosophical implications of quantum mechanics head-on.
Right.
It forces us to reconsider our assumptions about objectivity, causality, even the role of consciousness in shaping the world around us.
Yeah. We've talked about how quantum mechanics introduces uncertainty and probability into the picture. Does that mean the future is truly uncertain? Does it leave room for free will in a world that might be governed by chance?
Those are some of the biggest questions out there. And there's no easy answer. Schneeppet doesn't pretend to have all the answers, but he does a great job of laying out the different perspectives. He discusses the Copenhagen interpretation,
Yeah.
which suggests that the act of observation plays a role in defining reality. And then there's the many worlds interpretation,
Right.
which proposes that every quantum measurement creates multiple parallel universes, each reflecting a different outcome.
Multiple universes. Honestly, that one still makes my head spin a little.
It's definitely a mind-bending concept. And it's a testament to how far quantum mechanics pushes the boundaries of our imagination.
Right.
But it also highlights the fact that we're still in the early stages of understanding this strange and wonderful theory. There's so much more to explore, so many mysteries left to unravel.
And that's what makes it so exciting.
Absolutely.
As we wrap up this deep dive, I want to leave our listeners with a thought-provoking question that Schneeppet hints at in his essay.
Okay.
We've talked about how quantum mechanics challenges our classical intuitions. But what if those intuitions are actually limiting our understanding of the universe?
Ooh, that's a good question.
What if the strangeness of quantum mechanics isn't a flaw in the theory, but rather a reflection of a reality
Yeah.
that's far more subtle and interconnected than we ever imagined?
That's a fantastic question. It's like we're trying to fit a square peg into a round hole,
What?
forcing the quantum world to conform to our classical expectations.
Right.
But what if we need to expand our thinking, to embrace a new paradigm that allows for uncertainty, probability, and interconnectedness as fundamental aspects of reality?
It's a challenge to let go of our deeply ingrained beliefs about how the world works. But maybe, just maybe, by embracing the mystery and the wonder of quantum mechanics, we can open ourselves to a deeper, more profound understanding of the universe and our place within it.
Well said. And on that note, I think it's time for us to wrap up this deep dive. It's been an incredible journey, exploring the world of quantum mechanics with Yargo Schneeppet as our guide.
To our listeners, we hope this has sparked your curiosity and inspired you to continue exploring the mysteries of the quantum world. Keep asking questions, keep challenging assumptions, and most importantly, never stop learning.
Until next time, keep those minds curious and open to the infinite possibilities of the universe.
This has been The Deep Dive. See you on our next adventure.